Alright, let's work another example using the graphing technique I presented in the previous video to graph the function y equals 1/2 times sine of 2x minus pi. I just used the same image I had before for sine. Please note that the techniques still apply to cosine, and I'll do a cosine example in a moment. The way I look at these is picking out a cycle that has a beginning and an end. And usually we pick out like the clearest cycle closest to the origin just to make it easy to remember. Although really you could do this with any cycle for sine. So we want a complete cycle. Alright, so we're going to begin our complete cycle at x equals 0, ended at 2 pi. So here's my technique again. I'm going to find out where my new graph begins a cycle by replacing x in the formula for sine of x with the new angle 2x minus pi. So I want to find out where 2x minus pi will equal 0. Leave some space there for solving. And then I want to find out where 2x minus pi equals 2 pi to find out a new ending position relative to my substitution properties. So here I will solve 2x minus pi equals 0, so 2x equals pi, or I would get a new beginning position of pi over 2, so I'll hang on to that. Here I would have 2x equals 3 pi, or a new position of x equals 3 pi over 2, so I'll hold on to that. And side note, remember your new period, as a general rule, is a positive length, and it's the distance between where you end and where you begin. So I expect the period of this graph to be 3 pi over 2 minus 1 pi over 2, or 2 pi over 2, or simply pi units long. Okay, so this guy is less frequent than the previous example. Okay, and then lastly, what I will do is have a vertical compression by multiplying all the y values by the 1/2 coefficient. Okay? Alright, so let's see if we can get the graph mapped out, and then we can talk about period, amplitude, phase shift, and all that good stuff. Alright, so the graph. I'm going to do this. Let's pick a good color here. How about we pick bright red? Alrighty, so we're going to start our graph, and remember we're starting it as a sine wave when x is pi over 2. So I'm going to start on an intercept. I'm going to end at 3 pi over 2 with the pattern on the intercept. Halfway between pi over 2 and 3 pi over 2 is x equals pi, and I have another intercept. Halfway between pi over 2 and pi, I'll put a tick mark, and pi and 3 pi over 2, we'll note those values in a moment, we're going to go up to a value of 1, and then down to a value of -1. Okay, so you can see the period is much shorter. Now, all you have to do to get in the middle is average. Okay, let me put a little side note here. All right, so get in the middle. That's like midpoint on the number line. And the middle is that you average. So that would be the number pi over 2 plus the number pi, all divided by 2, which is 3 pi over 2, all divided by 2, or 3 pi over 4. Okay, now we could have saved ourselves some trouble by counting that that's 1/4, 2/4, and this guy's going to be 3/4. 4/4, so this guy is 5/4. Okay, so now we have the basic scheme of the graph. Goes up, goes back to the intercept, comes back down, the period's pi. Okay, so the last thing we have to take care of is the multiplication of 1/2, which is a vertical compression. So let's use another color. Let's say green. The intercepts have a y-coordinate of 0, so if you multiply 0 by 1/2, you still get 0. Here at the point 3/4 pi, comma 1, you're going to now have 3/4 pi, comma 1/2, like so. And 5/4 pi, multiplying the -1 here by 1/2, will now reach down and bottom out at -1/2. So you've got this little tiny graph, compared to the big one, that has a period of pi, and its amplitude, and I'll do this in green here, is its maximum value minus its minimum value divided by 2, or what's half the total height of the graph, which in this case it's 1/2 units. And again, notice, consistent with the vertical compression, so the amplitude's 1/2. Now we're going to talk about phase shift, and I'll do that in the next screen. So I want you to bear in mind that we've got a graph that starts at pi over 2, ends at 3 pi over 2, and has a period of pi, and bounces up to 1/2 and down to -1/2. Okay, so take a look here. We're going to start this graph over, and we're going to do this carefully together. We're going to start and end at pi over 2 and 5 pi over 2, and again, sign starts on an intercept and ends on an intercept. Period here is pi. Halfway between these two is an intercept. Halfway between left to right, we go up to the value of 1/2. Halfway between left to right, we go down to the value -1/2. Now, you can keep repeating this pattern on and on. So since the period is pi, all you have to do is either add pi to where you end. Okay, so if I add pi, which is 2 pi over 2, I would get 5 pi over 2. And I'd get another middle, and then left to right, high, low, okay? Or I could back it up and subtract pi units. Okay, so if I back up over here and subtract pi units, here's a new starting position. Now again, I'm working left to right. So this is begins, ends, middle, left to right halfway, go up to the max, left to right halfway, go down to the min. And we could do this on and on and on and on. Okay, we could do it for as long as you wanted to. We know that this thing repeats infinitely. Now the reason I actually backed it up some and moved it forward some, but mainly backed it up some, is to talk about phase shift. Okay, phase shift is where the original position, how it moved. Did it move totally left so many units or right so many units? Now remember what sine of x looked like. It started at 0, 0, and went through pi 0 and 2 pi 0 and so forth. Okay, this is just regular sine of x. And if I went backwards, I'd have, something along these lines like that. Okay, so I want you to notice that the pattern I'm looking for is this shape. Okay, I see it here. So I could call that my negative phase shift. But I also see the pattern start here. So I could think about that as a positive phase shift. But the most natural way to keep it straight is that we're shifting right based upon the minus sign we see inside. We know that this is a horizontal compression, and we saw that part with the period shrinking down to pi. So the most natural phase shift is found for sine or cosine by taking the argument of the function and setting it equal to the beginning position of the original cycle. And that's where we landed on, of course, the pi over 2. Okay, but again, that's because we're choosing sine to start at x equals 0, and I'm going to choose cosine the same way. So in this case, the phase shift is pi over 2. But it would not be incorrect to reconfigure the equation for the curve and make it look like it had a negative phase shift, and we'll get to that in the next couple of examples.